getting there. I'm going to start with the computer here. Let's see if it's going to work. Okay, hopefully you're looking at the NOC banner on that side. Is that what you're seeing over there? All right. Just a reminder, because it pops up in here in just a second. Maybe. They've got lots of stuff on our banner today. Maybe. Let's see if it gets there. We'll go there. Going to look at the calendar. If you look at the calendar, it's in there. And you will see that if we go down to January 20th, Martin Luther King Day, no classes. Woo! So we will not have class on Monday in here. Also, next Friday, I think I've already told you I'm traveling to an American Chemical Society meeting next Friday, which means you will have an online quiz in WebAssign. So we will not actually physically meet class on Friday, but you will have an online quiz. It'll probably get released on Thursday, and it will be due before class time on Monday, so you have the weekend to do it. But it will be in WebAssign, and so that'll be out there for you. So that's just as a heads up there.
What about lab?
No lab on Enid's side.
Okay.
No lab on Enid's side, because I will not be here, and that just makes life a challenge. Okay. Lab for you over in Tonkawa. I will have the second laboratory materials set up if you want to get ahead. Or if you want to come talk to me about the lab reports or something like that, I will be available on Tuesday. I will actually be on campus on Tuesday, so that's not a problem. Okay, if you go to engineering physics, you can get your link to WebAssign. Please, please, please. It looks like most of you have gotten in and can see your WebAssign, which is a good thing. Because if you click on WebAssign, and you get there, you will see, it will get here shortly. The first homework assignment is due Monday, even though we don't have class. You have your first homework assignment is due Monday at midnight. Please pay attention to the due dates and due times, because they will change throughout the semester. They will not always be at midnight. They will not always be at midnight, but in this case it is. So the first homework is going to be due on Monday night at midnight. Then I have pre-work items, and they're going to be due, one's going to be due before class on Wednesday, and one is scheduled to be due before, if we were to have met on Friday, before that class on Friday. Remember, homework is worth 25% of your grade, and this is where you have the opportunity to get extra credit. So just making sure everybody's got that part. Also, under course materials and assignments, we've got our week 1. You have in here the place to turn in your gumdrops in the flask. For those of you over here in Enid, I have the flask over here. If I open this up, you will see that it is due by 5 p.m. on Monday. So I need your guess and your rationale for how many gumdrops are in there, and it's worth 10 points. And it goes into the homework grade. So that's what's there as well. And I have some links to some pages out there to look at, and then Wednesday's lecture is here. So the January 13th lecture, I guess that was Monday's lecture. I thought I'd already uploaded Wednesday's lecture, but I haven't yet, so I'll have to do that, and then I'll have today's lecture as well. Okay? So that hopefully gets you guys back on board to where we're at and what we need. Any questions? Okay, because I'm going to switch over to the document camera, and we're going to start really diving into stuff. today. We're still kind of dealing with that unit on significant figures, estimations, some of the basics language that we're going to be dealing with. And so here is your trig review, since you kind of need a trig review, right? Big thing about trig that we're going to be working with is our basic triangle. So I've got my basic triangle here, okay? And we use the right triangle a lot. We also will use the law of cosines on occasion. So I've got just another triangle here. So that's just another triangle. We'll actually get that in here. Let me pull that part out. I'm going to do my law of cosines. So just as a reminder, if this is side A, this is side B, this is side C, this would be angle B, this would be angle C, and this would be angle A. Law of cosine says B squared is equal to A squared plus C squared minus 2AC cosine of my angle B. See if I can get it. Scroll back out a little bit so we can see a little better. And these kinds of things are going to be found in the appendix of your book. And so if I know two sides and an angle, I should be able to figure out the other information on that triangle. So we use the law of cosines. Also remember the law of sines will be if I have B sine of the angle B is going to equal A sine of the angle A, which is equal to C sine of the angle C. So just some basic trig information there. Now, this is our regular right triangle, and if I have this as the angle, we know that if I'm doing this in X, Y, and R, so this is X, this is Y, and this is R, the cosine of the angle is going to be X over R. The sine of the angle is going to be Y over R. And tangent of the angle is going to be Y over X. When we're dealing with our right triangle. So we're going to be using this right triangle over and over and over again. And we know that R squared is going to equal X squared plus Y squared. So I can figure out using my Pythagorean theorem for that. Now, those of you who like to work in X and Y, that's great. But we're in physics class. Physics class is going to do a bunch of different things, and not all the time are you going to be in a triangle that is nicely done as X and Y. So, I like to keep track of things like this. So here's my triangle. Okay? I like to do that. I like to make sure that I remember that as adjacent. This is my hypotenuse. This is my opposite. If I am using that angle, because a lot of times we may be working in a space that looks like that. So X and Y don't necessarily make sense, but the adjacent side and the opposite side certainly make sense. I may be working in a system that looks like that, given the angle that I've got. So if you like to work in X and Y, that's totally fine. I like to work it this way because that helps me keep track of where my triangle is, because we will be doing different types of space and working in different areas. So it's up to you which way you want to kind of keep it on track. So we're going to do a quick example here. Quick example. I've got a wall, and I'm going to use a large extension ladder. So this is my ladder. I've got it set up so that this is a 25-degree angle. My wall is 3.8 meters. I want to know what is the height of the ladder, or the length of the ladder. And how far away is this? So you can pick which one you want to do first. I know the opposite side and I know the angle, so I can figure out the hypotenuse. The sine of the angle is going to be the opposite over the hypotenuse. So if I'm solving for the length of the ladder, that's going to be the length of the wall that we've got divided by the sine of the angle. So that's going to be 3.8 meters divided by the sine of 25 degrees. And if I've plugged it into the calculator correctly, does not, oh, and I didn't plug it into the calculator correctly. Because one of the things I have to do is validate whether or not I am in degrees or radians. And this morning in my general physics class, we were working in radians. So my calculator was in radians, and it was a little odd because it gave me a negative value. And I'm going, I don't think the ladder has a negative value in length. Something's not right. I was in degrees, or I was in radians and not degrees. So if I do this, I end up with 8.99 meters as the length of my ladder. Now if I want to find the bottom down here, I can do it a couple of ways, right? We can do it a couple of ways. I know now the length of my other one, so I could use the cosine of the angle is equal to the adjacent over the hypotenuse, which means the hypotenuse times the cosine of the angle is going to give me my adjacent. Or I could use tangent, either or. That's up to you which way you want to do it. I'm going to do it this way. So I've got my 8.99 meters cosine of 25 degrees. And partially the reason I left it that way is because I had it already in my calculator, so it made it a little easier. And I get 8.14 meters is how far the ladder is away from the base of the wall. And obviously, my picture is not drawn to scale. Because that's more like a 30-degree angle. Maybe more like a 45-degree angle. So we're going to be using those kind of trig identities quite a bit. So hopefully that will help with the lab that you all have been struggling with. Okay. All right, so let's talk about a problem, and I think you guys have a similar problem. So let's I am not going to work the whole problem because I believe it is a homework problem or a partial homework problem. So what we have is we have a mountain. Okay, we got a mountain. And we've got a hiker that's walking towards the mountain. And we're going to make the assumption, if anybody's driven from western Kansas towards Denver, you kind of see this thing, everything's flat until you get right to Denver, and then it goes, boop, it's up. So we're going to make the assumption that we're far enough away that this is level, flat ground, and we're trying to measure the height of the mountain. So what we're after is the height of the mountain. Okay, so that's what we're after, is the height of the mountain. We're going to disregard how tall my person is, and we're going to make the assumption that we're in a level playing field here, and we get to the top of here, and we can measure this angle. And I'm going to say for grins and giggles, it's 30 degrees. Just for grins and giggles. Our hiker is going to hike a ways. Okay, and our hiker, let's say height. Let's go ahead and say it hiked 1 kilometer, and it's a reasonably flat area. So we know that we have 1 kilometer. And we're going to go ahead and we're going to sight the top of that mountain again. So we've sighted the top of the mountain again, and this time when we measure the angle is like 35 degrees. I want to know the height of the mountain. This is the height of the mountain, but I've actually done this because I'm just going to put in D. Because we don't actually really know how far away from the mountain we are. But now I've got a situation, right? I know my angles, I know that side. I have 2 variables, right? I have 2 unknowns. I don't know D and I don't know H. So in order to solve this, I have to have how many equations? Somebody speak up. It's 1:30 in the afternoon. You all should be awake. 2. Good. I have to have 2 equations because I got 2 unknowns, right? So this is a case of 2 equations, 2 unknowns. And so I've got to set up my 2 equations. So what 2 equations do I have? Well, I can do that the tangent of the angle is the opposite, which is the height, divided by the distance. When I'm using this case, the angle is 35 degrees. I also know that the tangent of the angle is equal to the height, except this time it's the distance plus my 1 kilometer, when my angle is 30 degrees. I now have 2 equations, 2 unknowns, and I now can solve for the height of the mountain. So this is another surveying technique. I can actually, and the fun part is, I just showed you the law of cosines, right? Well, we can actually use law of cosines on this one as well. So there's other ways of getting it. Because in that case, I can use law of sines, figure out this angle. I can do all kinds of fun things, and we can do a variety of different pieces. So there's more than one way to solve a problem. Okay? Some are quicker than others, some are less tedious than others, but there's more than one way to solve a problem. So like I said, I'm not going to work it all the way through, but at least I got the problem set up. And I will do that a lot, by the way, guys. Partially because of time constraints, partially because of everything else. I may set up a problem, I may even give you the answer, but I won't necessarily work out the steps, because that's a good way to figure out and learn how to get a few things. So let's look at, I told you earlier that dimensions are going to save your tushies. So I'm going to ask this question. Which of the following could be correct based upon just the dimensional analysis? So A, so which one?
A.
I got, somebody says A, everybody agree that it's A?
Yes.
It sounded like only one person agreed initially, but then I got several that said yes. How about over here, Enid?
Yep.
Yeah? Because I need a volume per a unit of time, right? If I'm doing a volume flow rate, I need a volume per unit of time. Volume is in cubes, so meters cubed per second is a reasonable flow rate. And that's probably something on the order of a flow rate through a dam or a possible flow rate over a waterfall, depending on where we are. So the height of the Transamerica building, what was the unit? What were the units given?
Meter squared.
Meter squared, which is it's an area. So height is not, so that one's definitely not. The time in fortnights, this one was bad because I didn't give you the unit as a fortnight. So, but what did I get? What kind of unit did I give you? I gave you a speed, meters per second. Or it could have been a velocity, but the velocity is fun. Speed and velocity are not necessarily the same thing, they're slightly different. The speed of the train, I gave it to you. What actually are those units, if anybody actually knows?
Acceleration.
It's an acceleration. It's an acceleration. And then density of, now this one's kind of a tricky one. If I'm doing a traditional density, it should be cubed. It should be kilograms per meters cubed. However, depending on what kind of densities that you're looking at, that's what we call, there's a surface area or a surface density. That, because we said a traditional density, we would think it would be in kilograms per meters cubed, but it could be a surface density, and then the square would be reasonable. Because if I'm looking at the surface density of atoms on a thin sheet, that is something that's reasonable. Okay? So we will see, and we will actually see linear densities as well. If I'm dealing with a wire, okay, down the road, I'm looking at grams per unit length. That's a linear density. So density can be kind of screwy. You have to kind of watch it, and you have to be looking at the problem, because linear density is actually given to you in terms of a lambda, and we'll see that, down the road a little bit. So I can give you, so this one could have been, if I were looking at a surface area or surface density, that's one thing that could make sense. So dimensional analysis also is going to help us out. So let's kind of look at, I'm just going to write down an equation. Y is equal to VT plus 1/2 AT squared. Okay. We will see this. This is a kinematics equation. Y is a position. And if Y is a position, it's likely to be in meters. Velocity is going to be in meters per second. It's going to be a speed, so velocity is in meters per second. Acceleration is in meters per second squared. And so if I look at this, I get Y is in meters. And if I'm doing this, I'm going to have my meters per second times time. And then I have my 1/2. And then I get meters per second squared. And I've got time squared. So I end up with meters and meters. Remember, I can only add like units. So if I'm adding things, I've got to have meters and meters. I can't have something. And if I've written my equation down wrong, let's say I put it in my cheat sheet and I write it down wrong like this, this will end up giving me meters, and this gives me meters per second. Obviously, I've done something incorrect. That is not a correct equation. So doing dimensional analysis is going to actually help you make sure that you've got things in the right spot. It also is going to help you a lot of times when we're dealing with stuff like this. So let's use density. All right, so I've got density. Density is going to be mass per unit volume. And let's say I get into a hurry, right? I get into a hurry and I'm going to do density divided by volume, and I'm going to say that that equals mass because I got into a hurry and I got sloppy, or I wrote it down wrong, or I was tired, and I get this. So density is in kilograms per meters cubed, and if I divide that by volume, this is meters, oops, ugly. This becomes meters cubed. This gives me some kind of unit that looks like kilograms, meters to the 6th. Well, guess what? That is not equal to a mass. So obviously I've done some arithmetic incorrectly to get that. So when I'm using I can use my dimensional analysis to really help make sure that I manipulate the equation correctly. Did I do something correctly? Am I getting the right units that I want to have? So it's going to help you out a lot. All right? It's going to help us out a lot. Then we have conversion factors. So I'm going to come back to that one. Come back to that here. We're going to do some conversion factors because this first chapter does conversions. And we have to. So I've got a crack in the wall. And it has been growing at a rate of 0.25 inches per year. What is this in millimeters per, I'm going to do it per hour, sorry. We're going to do it in millimeters per hour. Do it in millimeters per hour. Now, there are some conversion factors that you should have ingrained into your head. Okay? Some of them you just gotta know. And not everybody's are the same, but one of the ones that everybody should know off the top of your head, because it's a perfect, 1 inch is equal to 2.54 centimeters. And there are 10 millimeters in 1 centimeter. Okay? 2.54 inches per centimeter, or 2.54 centimeters is equal to 1 inch. And I got 10 millimeters into a centimeter, which is why we like the metric system, because I can do all these conversions all the time. Alright? And also, if you want to get a refresher, because you probably haven't used them in a while. Alright? Probably haven't used them in a while. We just did this calculation. My son called to ask to verify his math because it didn't sound right to him, so he wanted to do it. So we had 300 nanoliters, okay, 300 nanoliters, and we had 100 microliters. And I wanted to do the conversion factor. So I'm going to do this real quick because I want to show you that 300 nanoliters is going to be 10 to the minus 9. And 100 microliters is going to be 10 to the minus 6. And so these are now both in liters, so that's nice. Okay? But remember how you handle exponents. Okay? If I'm doing this, my answer now is 3 times 10 to the minus 3 liters. Because of how I can handle those exponents. So when we're dealing with the metric system, there are nice ways to do shortcuts. Okay? Nice ways to do shortcuts. I don't even have to put those into my calculator in order to get to that to get there right away. So you may want to kind of review using exponents because it shortcuts a few things. And if anybody wants to know, he was getting ready to do some PCR dilutions, and so we were working in nanoliters and microliters. Real tiny stuff. All right, so we want to get that. So I'm going to start with my 0.25 inches per year. All right, and I want to end up in hours, so I've got to do my conversion factors, right? So there's going to be 1 year, so I'm going to cancel out my years. There's going to be 365 days. And 1 day is 24 hours. So when I do that calculation, if I were to do that right now, I'd end up in inches per hour. But I'm going to go ahead and continue my conversion. So I want my 2.54 centimeters per 1 inch. And then I've got my I've got 10 millimeters is equal to 1 centimeter. And if I plug that into the calculator, I'm going to get 0.0000725 millimeters per hour. Okay, couple things, folks. Since it's probably the first time I've actually encountered it here, I use what's referred to as a Latin 7. And I use what is referred to as a Latin Z a lot, where I will put the dash mark in there. Because what happens is that a 7 or a 2? Or is it a squiggle on the page?
Question mark.
It could be a question mark even. So in order to help clarify what that number is, partially because I lived in Panama for 4 years, and the Latin 7 is very common in Panama. It also is very, very helpful to distinguish so we're not getting sloppy and everybody understands that that's a 7. So it's that I will use that for my numbers. Your text and several other texts now will do this. So I've got 100,000 here. They'll leave a space I don't like to use the space. I like to go ahead and keep my commas in there. So I keep that. And I generally always put a leading 0 in front of my decimal point, because you see my paper here, it's already got specs. If I write a number like here, is that 135 or is that 0.135? Because I have a spec on my paper, you guys won't necessarily know that. So I generally use the leading 0 to show you that that should be 0.135. Because what's going to happen to you folks is, as you start putting things together, your calculations and everything else have got to be clearly communicating. Yes, I know people's handwriting is a little difficult and different, and you will also notice that I use a mix of cursive and print. I still print most of the time, but we do have a bit of both. And I know that there are some places now that looking at cursive is going by the wayside. So be aware that those things that are out there. So hopefully most of you don't have any trouble with conversions. But, you know, every first physics chapter refers back to conversions, so we'll do one. I've got a pizza. Has an area of 36 inches squared. What is the radius? And the area in centimeters squared. Okay, there is no rhyme or reason as to why you do one or the other. I'm going to start with centimeters squared because it's easier. And we've just been talking about it. So I got 36 inches squared. And we know that 1 inch is equal to 2.54 centimeters. I've got to make sure that I square it in order to get my units to come up correctly. So if I do that, I end up with 232 centimeters squared. Area of a circle is pi r squared. So if we have this, so that's going to equal 36 inches squared. So r squared is going to be 36 divided by pi inches squared. R will end up being 8.6. No, sorry. What's the radius in the area? So if I do my 36 divided by pi. 36 divided by pi ends up being 11.5 inches squared if I do the square root.
Don't you just read your got your centimeter squared, 232 centimeters squared for the area?
That's for the area. 36 inches squared, 232 centimeters squared.
And whenever you're figuring out the radius in centimeters, you're doing the calculation there.
You can. I didn't specify units on the radius though.
What is the radius and the area in centimeters?
Well, I just said the area in centimeters squared. I asked what the radius is, so I didn't really specify. And I asked for the area in centimeters squared.
Well, the way the sentence should read, what is the radius and area in centimeters cubed?
No, that's actually a square.
Or squared, I assume.
Okay, but radius can't be in squares.
But what I'm saying is the way the sentence, the way you wrote the sentence, what is the radius and area in centimeters? I would assume the radius, we wanted the radius and area in the same.
Well, we can do it that way too. I agree, I intended, and actually that's what I calculated in my notes. The radius is 8.6 centimeters. If I do it that way. So you're correct. You're correct. And what you'll find, and this is one of those things that's going to frustrate the heck out of you guys. It'll frustrate the heck out of you guys. It frustrates the heck out of me, and I even write my own notes, okay? Is I'll come in, I have my notes laid out, right? I have my notes all nice and laid out, and then I ask a different question. Well, if you ask a different question, you get a different answer. In this case, I didn't specify the units for radius. It is implied that maybe I wanted it in centimeters, just like you said. It's implied that I may have wanted it in centimeters, but I didn't specify. And I'll guarantee you if I did this on a test, you all would come back and say you didn't specify what that radius is in, so I gave it to you and whatever. And I have been mean, cruel, and wicked that way too. Even as a student, I was a mean, cruel, and wicked that way. We had an instructor that drove us crazy. We loved him. And all of us went in and did it. And he asked to calculate the speed of something. And we gave it to him in leagues per fortnight. Well, he'd been harping on us about a few things, so we gave it to him in leagues per fortnight. We also gave him some volumes in hogsheads per, we gave him some volume flow rates in hogsheads per some weird unit, hogsheads per week or something like that. So, we did some really cool weird things. So you're absolutely correct. All right?
But what you're saying is don't do that to you.
Well, I'm just saying that I'll have to, we end up with it there. We end up with fun things like that. All right, so here comes a fun one. This is the human heart. The human heart pumps 5 liters of blood per minute. Okay, 5 liters of blood per minute. So we want to know how many liters is pumped per day. So we can do that calculation, right? So I got 5 liters per minute. We got 60 minutes per hour. And we have 24 lovely hours per day. And when I plug that into the calculator, I get 7,200 liters. Now, question is that reasonable? Well, first of all, think about 5 liters per minute. That's 2.5 2-liter bottles. Your heart is a pretty substantial pump, okay? Your heart is a pretty substantial pump. So the 7,200 liters actually makes a lot of sense. But the question now is, how big, just so that you guys can put it into your head, how big is 7,200 liters? So, let's put it into gallons. Well, 1 liter is approximately 0.26 gallons. So if I do that conversion, that works out to be 1872 gallons. It's a lot of milk, okay? Well, now I'm going to give you another reasonable thing, a standard American bathtub. And a standard American bathtub is approximately 80 gallons. A standard American bathtub is approximately 80 gallons. So think about that for a second. your heart is gonna pump about 23 and a half bathtubs.
You could calculate how fast somebody would bleed to death.
Doesn't take long. And it's called a sanguination, by the way, the proper term, sanguination. That's why if you hit an artery that you gotta get it stopped quick, because you only really have about 8 liters of blood, right? Isn't that what the standard amount is? I don't know, somebody have to Google it, but I think 8, for whatever reason, 8 sticks in my head. All right, the last time I did this calculation, because I always do this one because it's always fun, because people don't understand exactly how much rain is 1 inch of rain. Okay? So this time last year, we actually had a rainstorm. I have an 11.4 acre plot of pasture out in Osage County. Actually, I have, between the 2 plots I have something like 52 acres roughly, okay? And when we talk about an inch of rain, you're talking about the amount of rain that will fill 1 inch across, so it's 1 inch deep. That's how rain is measured. So if we got 4.1 inches of rain, okay, if you get 4.1 inches of rain, how much water is that? It really is how much water is that. So I'm going to do 4.1 inches of rain on our 11 acre plot. And so 1 acre, just because people don't remember it, 1 acre is roughly 43,560 feet squared. Okay? 1 foot is 0.3048 meters. Okay? 1 foot is, and we already know that 1 inch is equal to 2.54 centimeters. Okay? So we can calculate the volume of that, right? So I'm going to take my 4.1 inches, that's 2.54 centimeters per inch. 2.54 times 4.1 gives me 10.4, and I'm just going to leave it to 3 significant figures, 10.4 centimeters. All right, so I've got 43, 50, or 60, and that's feet squared. And 1 foot is 0.3048 meters. So if I do that conversion right there, I got to square that. So 43,560 times 0.3048 squared is 4,046 meters squared. I got to convert this. There's 100 centimeters to 1 meter. So we want that. So I'm going to take my 10.4 divided by 100. So I've got my area times my height is going to be my 46 times 0.104. This gives me, oops. That gives me about 420 meters cubed. It's 420 meters cubed of water. And it turns out 1 meter cubed of water is 264 gallons.
Wow.
That is 110.87 gallons of water that fell in a 24-hour period. Now, when with the last hurricane that came through Houston, I actually calculated the number of Kaw Lake volumes that fell in a 24-hour period. It's a lot of water.
How did you get from 420
Meters cubed,
to 110,000?
1 meter cubed of water is 264 gallons. And so you just multiply the 264 times 420. Alrighty. We got through estimates, conversions. We started looking at our trigonometry. That should get you pretty well through the first chapter. And we'll see everybody on Wednesday.
Do you do it?